Welcome. Einstein's theory of general relativity was published on 1915 by Albert Einstein. Since then, there have been all kinds of attacks on the theory. Most of them, most of them are nonsense and discarded. But there was one attack by a contemporary of Einstein. His name is Erich Krettscmann. His attack on theory is still around, and most people believe that there is some validity to his attack. So my goal is to discuss Erich Krettsmann's attack on general theory of relativity. So what Erich Krettsmann is saying. So before that, I want to give some background information about general theory of relativity so that you understand his attack. So, Einstein's theory of relativity based on something called general covariance. What it means is that Einstein said that natural physical laws should not have anything to do with our coordinate systems. Let's say I have a nice coordinate system, x, y, z, and time axis and all that. Another person has another coordinate system, and it is moving, and according to him I'm moving, and according to me he's moving, and but the physical laws should be same for me and for him. Let's say he has a set of equations and I should have the set of equations. Both equations should be the same and they should work, because physics cannot change just because I'm going in a rocket. That's what Einstein said. Now the time can change. If you're going in a rocket, the time would slow down. That's a different story. But according to him, my time would slow down. According to me, his time would slow down. So that's a different issue. But the basic physics for me and somebody else, that is moving, and that would be called a different frame. He has that one observer has one frame and another observer has another frame, and both observers should have the same physical laws. And also Einstein said that there is no preferred background reference frame. There's no preferred background reference frame. And in the case of Newtonian theories, that the background reference frame has to be a three-dimensional, and the time and space cannot be together. They have to be separate. Time is going on its own. Just because you move, the time would not change for each observer. So Einstein formulated now the physics should be the same for all inertial frames, and there has to be a way to transform my values to another observer in another reference frame. And this transformation is called tensor transformation, because the equations are tensors. Tensors are a bunch of vectors. The vectors are coming together in a certain pattern, and then you would call it a tensor, like the stress center tensor. You have the vector for area and vector for force, and they are in a certain manner. Similarly, in Einstein's theory, you have the Ricci tensor and a Ricci scalar. Those are the two things that describe the curvature. And those tensors have a certain form, and when I transform them to another coordinate axis, another frame, and then the same laws, same physical laws that are governing me should govern him as well. So that was called general covariance. That is, the physical laws are same in all reference frames, and there has to be some way of transforming the coordinates from one frame to another, coordinate transformation. So this is Einstein thought that was one of the biggest challenges to overcome to make it general covariance. But this is what Erich Krettsmann said. He said that you could pick arbitrary rules and then some mathematical trick you could transform to another coordinate system and bring it to a covariance form. So Erich Krettsmann said it's not a big deal. The big deal is you have to develop your equation, which he didn't say, but which he implied, that through some kind of fundamental step-by-step process, which Einstein didn't do that. His ideas did not come from any deeper theory. He picked that on one side, he said that on one side of his equation you have the stress energy tensor, which is matter and energy. On the other side you have the space-time curvature. Why is the space-time curving? Because of the matter. So if you don't know, and that's how Einstein formulated his theory. Of course, there is the cosmological constant which he added later on. So, um, again, general covariance is where you have two coordinate systems, and you have one set of tensors for one coordinate system, and you have tensor transformation, and they have very specific way to transform the covariant tensor. So once you transform to the other coordinate system, the other person also would have same physical laws. But what Erich Krettsmann is saying, that you could do that to any arbitrary theory and you could bring it to covariance form. But Albert Einstein gave a challenge. He said, okay, he didn't say that way, but he implied, try to do that to Newton's theory and see what happens. It may not be a viable theory. And people took the challenge and they did that to Newton's theory, and they made, it's called Newton's Cartan theory, and it was made into a covariance form. And it didn't, of course, it didn't work as well as the Einstein theory of relativity, or general theory of relativity. And some people don't like the word relativity either because of the issue that comes along with the covariance form. So it would be, most people prefer to call Einstein's theory of gravity instead of relativity. But the old name is still around. So I'm going to read what Einstein said. I believe Erich Krettsmann's argument to be correct, he agreed, but the innovation proposed by him not to be commendable. That is, if it is correct that one can bring any empirical law, because Einstein's theory of relativity is an empirical law, there's no theoretical background that because it would be quantum gravity. If someone were to build up from bottom up, it would be quantum gravity, which has not been found by anyone yet. That's way down the future. So any empirical law into general covariant form, the principle still possesses significant inherent force which has already proved itself brilliant in the problem of gravitation, and rests on the following: of the two theoretical systems compatible with experience, the one to be preferred is the simpler and more transparent from the standpoint of absolute differential calculus, that would be the tensor transformation. Let one bring Newtonian gravitational mechanics into the form of absolutely covariant equations, four-dimensional, and one will certainly be convinced that principle excludes this theory, not theoretically but practically. And Einstein was right in one aspect, wrong in another, that if he's implying that it's impossible to bring to general covariance form, Einstein was proven to be wrong, because they did came up with general covariant form for Newton's theory. But he's correct that did it is theoretically possible, but it was not practical in the sense it didn't comply with the experimental results. So the Einstein argument, he further goes, the principle of general relativity imposes exceedingly strong restrictions on the theoretical possibilities. Without this restrictive principle, it would be practically impossible for anybody to hit on the gravitational equations. So, basically, just because you guessed it, it doesn't really mean that it's going to work, layman term. So Einstein is saying, first of all, it's very difficult to bring it to covariant form. He agrees it can be done, but still it may not work. So that was the argument, and Einstein was right. Newton-Cartan theory is not as good as Einstein's theory of general relativity. But the argument that general covariant form is the main reason for us to believe that it's correct is not true anymore, because of Erich Krettsmann is saying that it can be done not only for general theory of relativity but for any other theory, and it has been proven that it can be done for Newton's theory of gravity as well. Thank you very much for listening.